Hi everybody, welcome back to Chem 121. It is Monday of week 7, and there's not that many weeks left in the quarter, it turns out. We have, this week, 3 more weeks, and then finals. So, like, after 5 total weeks, it'll be summer vacation. Blink and you'll miss it. It'll be over before you know it. So too will Maya meowing. She just heard me talking, and now she's running into the room. Hi, Maya. Yes, I'm teaching. Yeah, oh god. I'm wearing a headset, but I can just hear meow. So sad. What do we have on the agenda? There is a lab due this week. Lab worksheet number 3. It's about molecular models. That's Unit 5 stuff. Make sure that you get that in by the Wednesday deadline. That is a soft deadline. If you need another day to do it, the assignment will close on Thursday, and that's no problem. Over the weekend, I finished grading all the labs for lab number 2. Maya, Sandy says hello. I don't know if she heard you, but that's okay. I finished grading all the labs over the weekend, so all your lab 2 stuff should be on Canvas. Click on the assignments and then click on lab number 2, and you should see where I have uploaded the documentation. Not the documentation, your worksheet that you turned in. I graded it and uploaded it again. As well as all exam grades. So if you took your exam on the scheduled day, your score was posted early. If you took the exam later, due to whatever circumstance, it is fine. I finally got around to releasing the scores, I want to say Saturday. If you can't see your score for some reason, like it's just blank or it's not showing up, in specifically the one that's out of 75, let me know. I will fix that. The one that's out of 83 will never appear. That is just your raw score without me doing any tinkering to it, so don't worry about that one. The one out of 83, pretend it doesn't exist. It should also say it doesn't count towards your final score. Something like that. We left off here. Oops, that's not what I meant to do. We left off here when we finished off last week, I believe on Wednesday. We did chemical equations. I showed you how to balance equations. You balanced all the things. We also did some calculations involving mole to mole within like a formula. So like if I have 1 P4O10, there are 10 oxygens. So therefore in 1 mole of P4O10, there would be 10 moles of oxygen. That sort of thing. And then we did like grams to moles to moles to grams. Those calculations should be familiar. Hopefully you are proficient at doing them, because we're going to now do those 2 topics together. We're going to put chemical equations together with the mole to mole concept, because a chemical equation like this one represents a quantity of molecules. And just like I could say there is in 1 molecule of NH3, there are 3 atoms of hydrogen from previously just looking at this, what I could also say is 1 molecule N2 reacts with 3, oops, sorry, I'm trying to conserve space here. So reacts with 3 molecules of H2 to form 2 molecules NH3. And I need each of these parts to do the reaction. If I'm missing any one of them, the reaction doesn't work. So in other words, I could say 1 molecule of N2 needs 3 molecules of H2, and that will create 2 molecules of NH3. And because I need all of these parts, they must all be equal for this reaction, because otherwise it wouldn't be balanced, right? So if I have 1 molecule of N2, I can run the reaction. If I have 3 molecules of H2, I can run the reaction. If I have 2 molecules of NH3, the reaction has been run. Now, I'm just considering these independently for each part. Do I have this ignoring everything else? Yeah. Do I have this ignoring everything else? Yeah. Do I have this ignoring everything else? Yeah. Now, because I've made these into an equality, I can take any two and set them equal to each other, right? And what I can also do is I can do this. I can just times everything by a mole. So following the same logic and algebra that we did for the mole-to-mole conversions in the formulas chapter, or the formulas unit, with the P4010 and the N205 and all of those things that we did earlier, we can then make relationships between any two components of a balanced chemical equation. So for example, maybe I did a reaction and I wanted to know how much N2 would react with how much H2. Well, I could use the relationship 1 mole of N2 requires 3 moles of H2. Or maybe I just want to look at the conversion between how much hydrogen can potentially make how much ammonia. And then I could make the relationship 3 moles H2 equals 2 moles NH3. I could pick any two I want. Any two at all. Whatever one that I'm not looking at, we're just going to assume that there is abundant of it and it doesn't affect our result. Now, you can actually do this with all three at once, but this is an introductory chemistry class, so what we're going to do is we're just going to stick to two. I'm going to pick two things. I'm going to give you an amount of one. I want you to tell me how much of the other is needed to do the reaction, or how much of the other is produced if it's a product. All right. Oops, let me clear all that off the screen here. And so this is just saying what I said before, where I can make it a sentence, and I can make any relationship I want between any two things. Now, there's only 3 different relationships here. If you have more reactants and more products, then you get more relationships. But what's important here is that, just like before, where we went moles to moles of something, on that chart, and you know what chart I'm talking about, it's the one that looks like this. We had moles of A and moles of B here. Whatever I want to pick, I can call that A, and whatever I want to change it to, I'll call that B. And then we can just convert from A to B using the chart again. So what we're going to do is we're going to do more of those types of calculations, as you can see right here. And we're going to use a balanced chemical equation to do that. So you need the equation in order to do this. So let me write it down, because for some reason it doesn't appear here. Oops, that didn't work. There we go. So we got N2 plus 3H2, 2NH3. That doesn't really look like an N. Let me fix that. I know why they're all upset. So I had to go and pick up something from UPS today. And my cats are both excited and annoyed that there is now a box where there wasn't one. But it's not an open box, so they can't go in it. So they're very upset about this. Because they keep pawing at it, they keep jumping on it. They want it in the box, but they can't because I haven't opened it yet. So I apologize that you have to deal with me shouting at the cats every 20 seconds. All right, so we've got the equation on the board here, and what we need to do is we need to figure out what we're starting with and what's our goal. So I gave you 5 grams of nitrogen, and I want to know how many grams of ammonia can be made out of this if there is an excess amount of hydrogen. So what does this mean right here, first of all? If you see the word excess, what that means is that excess hydrogen is present in abundance. There's tons of hydrogen in this reaction, and you don't have to worry about it. You're going to use up some of it, but it will never run out because it is an excess. The other one that will run out is the one that's indicated, 5 grams of nitrogen. After you run out of nitrogen, the reaction stops because there's no more reactant, right? So what this question is asking specifically is, if you have 5 grams of nitrogen with an excess of hydrogen, how much ammonia will be made using up all of the nitrogen? So we're going to go from here to here. Now, what that means is that on our chart here, we're going to start with a mass, and we're going to go to a mass. And I'm going to call A nitrogen, and I'm going to call B ammonia, because those are the things that I'm working with. So let's write out all of the relationships that we're going to need for this reaction. So if I go from grams to moles, moles to moles, and then moles to grams. Sorry, you can't really see the arrow there, but that's okay. For this first relationship right here, I need to know the number of grams of A. A was nitrogen in a mole of N2. And if you go to Lentech or grab a periodic table, you can calculate that out. And I might as well go to Lentech because I'm going to need it in a second here. Nitrogen is 28.01. So we'll write that in there. Then I need to do this relationship here. And that's going to be moles of A, which is moles N2, to moles of B, moles of NH3. How many moles of each? Well, according to this balanced equation, right here, for every 1 nitrogen I put in, I get 2 ammonia out. So for every 1 mole of nitrogen I put in, I'll get 2 moles out. And then finally, for the last relationship here, to go from moles to grams, where moles of B is ammonia, in 1 mole of ammonia, how many grams are there? According to Lentech, there are, it's like 17 something, right? Oops, that's not, gotta capitalize the H or it doesn't recognize it. 17.03 grams of ammonia. All right, so we've got all the setup done. So now what we need to do is, well, that's not going to work. Let me crop it properly here. We'll put this up here. And then this didn't appear because I didn't actually click it. So there we go. All right, so we'll get our starting amount here. Oops, that's not a color that I can see. Ah, that didn't work. There we go. There's the amount that I'm starting with. So I'm going to do the conversions in order, 1, 2, 3. So here's conversion number 1. I'm going to turn grams of nitrogen into moles of nitrogen. And then conversion number 2, we're going to turn moles of nitrogen into moles of ammonia. And then finally, we're going to turn moles of ammonia into grams of ammonia. So from 5 grams of nitrogen, how much ammonia could you potentially make? Since we're combining the nitrogen with hydrogen, we should get more mass than we started with, because the remaining mass would be hydrogen that was added. And so we'll just fill in all the numbers now. So this was 28.01. 2 moles ammonia is 1 mole N2. And 1 mole of ammonia is 17.03 grams. And let's get the calculator. Five 0.00 times 1 times 2 times 17.03 divided by parentheses 28.01 times 1 times 1, close parentheses, I get 6.08. And that answer makes sense because I used all the nitrogen, so I have at least 5 grams of nitrogen in my ammonia. And then a little bit extra mass from the hydrogen. Just in case you're wondering why we got a bigger number. It's because I put the hydrogen and the nitrogen together to get the ammonia. All right. So that was one example using ammonia. So let's clear all this. There's my path, and there's the answer. All right. I'm going to give you a second example, and again, I'm going to put the reaction on the board here because for some reason it's not here. I really should have put it here. And I want you to try and do the same thing because this is the exact same process. I'm going to use 2.75 grams of hydrogen this time. How much ammonia do I make out of that? I don't know. It's a product, but if I don't tell you anything about the product, we're not going to solve for it. Instead, I want to know how much nitrogen is needed. So, you know the relationship between hydrogen and nitrogen using mole to mole. So, follow the same process that we just did to solve the first problem to solve the second problem here. I'm going to give you about 5 minutes to do it, and if you get stuck, type something in the chat so I can help you, okay? We'll go over the answers together after this. See you in a bit. How are we doing? Let me know in the chat. I'll give you about 2 more minutes. Get as far as you can, and then we'll go over the answer. All right, let's go over the answer here. I think you almost have the answer there, Sarah. So we're going to say A is hydrogen, because that's the number we're given, and we're going to say B is nitrogen. Now it's mass to mass. Whenever I say how much, usually I preface it with a unit, but if I don't, I'm almost always intending to do mass. If you're not sure, let me know. There's our starting point, there's our ending point. All right, so number 1, grams to moles. So 1 will be grams of hydrogen, moles of hydrogen. In 1 mole of hydrogen, there are, and it's something, right? H2. 2.016 grams of hydrogen. For 2, we're going to go moles of hydrogen to moles of nitrogen. And you can see in the balanced equation up here that for every 3 moles of hydrogen I have, I also need a mole of nitrogen. Yeah, that looks like the right answer. That's what we're going to get to, I believe. Then number 3, we're going to do moles of nitrogen to grams of nitrogen. In 1 mole of nitrogen, there are 28.014 grams of nitrogen, or 28.02 actually. I'm just trying to do it from memory now. That's good enough. And so we'll do the same thing. I don't even need to clear the old problem. We'll just leave it there. That's fine. Oh, my Photoshop barked. There we go. Let's get a new color, though, so you just know that we're on a different problem. All right. I already forgot how much hydrogen we're given. 2.75 grams. Okay, so 2.75 grams of hydrogen. We're going to set it up in pretty much the same way. We're going to go grams of hydrogen to moles of hydrogen so that the units cancel. Then moles of hydrogen to moles of nitrogen. And moles of nitrogen to grams of nitrogen. And then we'll fill in the numbers with what's up there that you can see. So 1 mole of hydrogen is 2.016 grams of hydrogen. If I use 3 moles of hydrogen, I also need 1 mole of nitrogen. And in a mole of nitrogen are 28.02 grams. And we'll punch it all in the calculator. 2.75 times 1 times 1 times 28.02. You don't actually have to do the times 1s. Divided by parentheses 2.016 times 3. 12.7 grams of nitrogen. I'm using the wrong end of the pen. That's why it's not working. All right, that's the process. Let's do another one. I'm going to give you a different reaction here. So for this reaction, we're going to look at sodium azide. Sodium azide is used in the airbag in your automobile. Basically, what happens is when you purchase a car with an airbag, the airbag is connected to a tube that goes through the driver's steering wheel column. And that tube goes to a small chamber in your engine area, in the hood of your car, that has sodium azide in it. That sodium azide is connected to a circuit, and the circuit is connected to your bumper. When your bumper collides with something with enough force, the bumper will go back and it will complete the circuit. What that does is it ignites the sodium azide, and this reaction happens. When you do this reaction, you produce nitrogen, which is a gas. The gas then fills that chamber with the sodium azide in it, and then goes up through your car, through the steering column, to fill the airbag to deploy it, so that you then bump into the airbag with your head instead of the steering wheel, which is a lot more dangerous. All right, so that's the gist of how steering wheel airbags work. Same thing happens for like side airbags and stuff like that. If an impact is detected, it sets that off. So yeah. So the question that we have here is a little different than the ones that we've had before. We aren't doing mass this time. Instead, I want to know what mass of sodium azide produces 253 million molecules of nitrogen. Now, you might think 253 million molecules is a lot of molecules, but it turns out that molecules are so small, you're going to get this teeny, teeny, teeny mass to produce that. So when you get your answer, if you get a really small number here, you're doing it correctly. But you are going to use Avogadro's number here. So look for where you're starting, and it's not grams. You're not starting with grams this time. And then look for where you're going. I'm going to give you about 5 minutes to try this, and we'll go over the answers together after that. See you in a bit. How we doing? 1 or 2 more minutes, we'll go over the answers. Let me know if you have any questions. All right, let's go over the answer here. So I got to write up here, unfortunately. Well, I guess I'll put it over here. So in this case, we want to know, and I've sort of tried to obfuscate this by rearranging the way that the question is stated. So I have this many molecules of N2 that need to be made. And I want to know what mass of sodium azide will make that. So my A here, which is my known amount, is going to be nitrogen, because I know how many molecules of that I made. My B amount is going to be sodium azide, because that's what we're solving for. And since it's molecules, we're going to start here. And I want to know the mass, so we're going to end here. So we're going to go like this. So here's relationship 1, 2, and 3. So relationship 1 is going to be particles of N2, which are molecules, and moles of N2. And we know that in a mole of anything, there are Avogadro's number of those things. Then we got relationship 2. For relationship 2, we have moles of N2 to moles of sodium azide. And according to our balanced equation here, for every 3 nitrogens we make, we need 2 azide, sodium azide. So there we go. And then the last relationship down here, number 3, will be moles of sodium azide to grams of sodium azide. And in a mole of sodium azide, we'll go look up the molar mass. Oops, that's also not it. There we go. NaN3. There are 65.01 grams of sodium azide. All right, we got all the relationships set up, so now let's go to the problem. And we'll just scroll this down a little bit. So we'll set it up just like we've been doing so far, except instead of starting with mass, we're going to start with particles, because that's what's given. So we have 253 million, so that's this, 2.53 times 10 to the 8 molecules of N2. And then we're going to convert molecules of N2 into moles of N2. Those cancel out. Then we're going to do moles of N2 into moles of sodium azide. Those cancel out too. And then finally, we'll do moles of sodium azide into grams of sodium azide. And now that we got the unit we want, we can run the numbers. So in a mole, there are Avogadro's number. That should be a 3. Doesn't really look like it. Let me fix that. There you go. Then the relationship from moles of N2 to moles NaN3 was 3 moles N2 to 2 moles NaN3 from our balanced equation that we had before. And in a mole of sodium azide, we had 65.01 grams. We can type all of that in the calculator now, so let's do that. 2.53 times 10 to the 8 times 2 times 65.01 divided by Avogadro's number times 3. 1.8 times 10 to the minus 14. 1.82, actually. So that's what I got. Stop that! It's a box! Sorry. He really wants in the box. But he has like 74 boxes in the living room. Like, I keep these boxes purposely for my cat. There you go. That's the answer I got. So, Sarah, yours was close. Double check that you didn't lose a number in your calculator or something like that. But otherwise, you're definitely on the right track. Somewhere a number got misplaced. All right. I have one last set of these for you to try. Here's my reaction that I'm going to give you. So I'm going to give you KClO3. KClO3 is a really common reaction done in the lab because when you heat it, high temperature, it starts to bubble and fizz and oxygen comes out and you get KCl. So it's really cool to like study gas law reactions because you can get a controlled amount of oxygen out of it by just heating the hell out of the potassium chlorate. All right. If a student uses 0.522 grams of potassium chlorate and decomposes it completely, how many grams of KCl are in her test tube? Now, notice that I didn't balance the equation here. And obviously it's not balanced because you can't have 3 turn into 2. Like, that's not something that's allowed. So you got to balance the equation. I can't actually draw on the screen because my calculator's on the tablet. So make sure that you use that. And then what I want you to do is do the equation again with the same sample. So use this amount for both exercises. How many grams of oxygen will be released? And then what I want you to do is look at your answers that you got for these two problems and ask yourself this question. Has the conservation of mass been verified by this experiment? Look at your numbers afterward and see if they compare to this number in a reasonable way. And yeah, that's all I have. So I'll put the homework practice up here too. Go ahead and try these problems. I'll give you about 6 or so minutes. If you have a calculator issue, the best thing that I can think of for you to show me is tell me what answer you got, and then take a picture of your calculator and send it to me, either in Discord or on email. If you're off by like a power of 10 or something like that, or if you aren't using parentheses, if I can see your calculator, I can advise you. Okay, so you can go ahead and do that during this time period, or during the break or whatever. Because I think after this we're going to take a break because we're almost at an hour. All right, I'll let you try these problems. See you in a bit. We'll go over the answers in a few minutes. If you get an answer for the oxygen one, post that one too. And then, Micah, if you got my email, let me know if that fixed it. Oops, when I hit the emoji keyboard, you can see kind of what I'm doing down here. Where's the one that I always use? There he is. Boop. There's the ogre. Okay. Let's go over the answers here. I gotta clear this out, and we'll go to wrong window. There we go. All right, so let's do the first one here. Oh, Maya is here again. Hi, Maya. All right, so this first problem, I don't have the little chart here, unfortunately, but we can just sort of blueprint it out. So I'm giving you a mass of KClO for each problem. And for the first iteration of this, we're trying to figure out how many grams of KCl there are. So we're going to turn this into moles. Oops, sorry. Forgot a number there. And then we'll turn this into moles. We'll turn it into grams. And so the relationships that we have here would be grams of KClO3 equals moles KClO3. And in 1 mole of KClO3, there are... I gotta find Lentech. It got buried because I'm answering emails from other faculty during the break. KClO3 is 122.55. Let's write that down. And then for moles of KClO3 to moles KCl, well, I need numbers to go here, but we didn't balance the equation, or I didn't balance the equation, so we got to go back and do that. So, balancing the equation real quick, you should get something that looks like this. 2, 2, 2, 2, 2, 3. There we go. I'm just double checking. Is that right? 6, 6. Yeah, okay. So that means that for every 2 KClO3 you use, you get 2 KCl when you're done. And then we can do moles KCl to grams KCl. And in a mole of KCl, there are... Oops, I don't know what that is. I mistyped it. 74.55. Oh, I really didn't give myself enough space there, did I? There we go. Now we can do the dimensional analysis. So I've got 0.522 grams KCl03. We're going to turn grams of KCl03, I don't know what happened here, into moles of KCl03. And then we'll turn the moles of KCl03 into moles of KCl. And then we'll turn moles of KCl into grams of KCl. And now we can run the numbers because we've got all the units set up. So in 1 mole of KCl03, there are 122.55 grams. That's what we just did right there. For 2 moles of KCl03, you get 2 moles of KCl out. That's these. And then finally, in 1 mole of KCl, there are 74.55 grams of KCl. That was this last one. We'll punch it all in the calculator. 0.522 times 2 times 74.55 divided by parentheses 122.55 times 2 close parentheses. I got 0.318. That was our KCl. Now we can do the same thing with grams of oxygen, so we'll scroll down. And we'll do the process again. So we start with grams of KClO3. Now this time I want grams of oxygen. Same exact process as before. And we'll write the relationships just like before. Now this one hasn't changed because it's grams of KClO3 to moles KClO3. And I already figured out what that number was. 122.5. Oh, it's right here. 122.55. And then we'll do moles of KClO3. This is too close, actually. Hold on. To moles of oxygen. And according to our balanced equation up there, for every 2 moles of KClO3 I put in, I get 3 moles of oxygen out. And then finally down here, moles of oxygen to grams of oxygen. 1 mole is just 32 grams of oxygen. Now we'll set up our problem. Same as before. In fact, the first step is exactly the same because we're turning it into moles. So no big deal there. Then we'll turn moles of KCl into grams of KCl. Oops, no, we're not doing that. What am I doing? Sorry. Moles of KClO3 becomes, what are we doing? We're doing this one. Moles of O2. And then we're doing moles of O2 into grams of O2. So those are our 3 steps there. Let's go fill in the numbers. This is the same number as before. We got 2 KClO3 to 3 oxygen, so we'll put those in there. And then a mole of oxygen is 32 grams. And when I do all that math, we get 0.522 times 3 times 32.00 divided by parentheses 122.55 times 2. And I get 0.204. And then the last question shown here is, has the conservation of mass been verified by this experiment? What that means is that is the mass that you put in the same as the mass that you get out? So let's check that real quick. So I should have this much mass total. So if I take the KCl that I solved for and the O2 that I solved for, and I add them together, I get 8 and 4 is 2, 2, 5. So this is the mass of the KCl and the oxygen produced. And look at that. Exactly the same. So we have verified the conservation of mass. And in fact, all the equations that you do will follow the conservation of mass. All the matter that you start with will be accounted for as all the matter that you end with if you solve for all of the products. And there is only one reactant, like there was in this case. That's just a feature of stoichiometry and how the calculations work out. Now, again, you can only do this for a reaction, and we'll go back to this window here, where I have one reactant and I know its mass, and I solve for the mass of all the products. If I wanted to do this with multiple reactants, I'd have to know the masses of both, and there's a little bit of extra work that you have to do in that, but we're not going to do any examples of that in this class. It still does work, though. But it's kind of cool that that works out as it does. All right, there's the homework practice. I believe that's the end of chapter 6. So there should be a dancing orc on the next slide. There he is. Oh, and everything stopped. That's okay. All right, blank screen. Break screen. All right, we're going to take a break. When we come back, we'll start chapter 7, which is gas laws and other fun stuff. So I will see you in 10 minutes for that. Alright, we're back. Let me wind this down here. There we go, that popped up. Alright, so we're now in Chapter 7. So what that means is, 1, you'll need to get your Chapter 7 slides out. And 2, I'm going to post the quiz for Chapter 6 after class is over. So that'll be due a week from today. And it'll cover Chapter 6. So there we go. Chapter 7 is about different phases of matter and some various things that we can look into. In the first section, we're going to explore gases. And that's going to be what we spend the rest of the day on today, is just talking about gas laws. Gas laws are pretty straightforward. There's a little bit of algebra, not anywhere near as complicated as the stoichiometry part that we just finished. So we're going to kind of ease up on the math for the rest of the quarter. I think the hardest part of the math is behind us. Like, we're done with that. So if you can make it in Chapter 6, you can make it anywhere in Chem 121, in my opinion. After we do the gas laws, we're going to talk about how phases change. For instance, like, what does it mean to change from a solid to a liquid to a gas? There are terms for that. There's energy involved. We're going to discuss that briefly. And then we're going to talk about how phases stick together. So, like, what holds molecules of water together in a solid? Like, if you put it in the freezer, you get ice. If you put water in the freezer, you get ice. But why does it stay as a solid at that temperature? Like, aren't the molecules independent? Like, something must be holding them together. What is it? And we'll talk about that. All right, so let's talk about matter at probably the highest level of detail that we can really do. So let me first clear off the screen real quick. Don't worry about what's at the top, which is nothing right now. Oops, I didn't click over here. All right, we're going to explore matter in terms of what atoms do. So if these are my atoms, here's a bunch of atoms that I've got of something. Now, they could also be molecules, but we'll just assume that they're atomic. Now, if this is a gas, my molecules are not stationary because they would all then fall to the ground and we'd all suffocate if gases didn't move around, right? So gas particles must be in constant motion. And they can even bounce off of each other or whatever. So particles in a gas bounce all over the place at really, really high speeds. We're going to move that over here. Oops, there we go. They are always in constant motion. The word in science that is used for motion is called kinetics. Something has kinetic energy if it is moving at a given velocity. Velocity. I can't words today. I'm sorry. If a molecule or atom is moving at a given velocity, it is said to have kinetic energy. And kinetics is just things that move. Now, what about a liquid? In a liquid, all of my molecules are kind of clustered real close to each other in a container. Now, I'm not going to fill the container, but you get the idea, right? Now, are these molecules completely stationary? Well, if they were, then the liquid wouldn't flow or move in any way, right? So all of these molecules are also moving in various directions. And heck, they can move up. So this would be evaporation, when molecules escape the solution, but not many of them do that. Most of them stay constrained to the liquid. So liquid molecules are also always moving. However, they are not moving as fast as gas molecules are, because if they were, they would go sailing apart at ludicrous speeds. Molecules move around, but they are constantly colliding with other things, so they are not moving anywhere near as quickly. Finally, in a solid, if this is my solid and all my molecules are arranged like this, if my molecules were to move, they wouldn't be a solid anymore, right? The matter would flow. The molecules could be displaced if you touch them. But when you put your hand on your table, or you sit on your chair, or whatever interaction you have with a solid, you notice that you don't fall through the solid as all the molecules move out of the way. Molecules stay there, right? So in a solid, molecules don't move about. But is that all the motion that they have? Like, are they completely stationary? No, what they tend to do is they tend to vibrate. So they wiggle. And so they have almost zero kinetic energy. They have a little bit because they're trying to move. Like if I hit the table vibrates a little bit, and that vibration comes from all of the molecules vibrating as that wave of energy pulses out through them from the impact point. But they don't dislocate from their structure. If they moved around and retained their shape more or less, they would be a liquid. So, kinetics is the study of how things behave based on their ability to move. And so what we say here is that we say gases which move freely and a lot have high capacity for kinetics, or high kinetic energy, which we're going to abbreviate Ke. Solids, on the other hand, can't move at all, so they have very low kinetic energy. And then finally, liquids are sort of in between. They're moving a little bit, but not fast enough to separate themselves all apart. So we have sorted the phases of matter based on their ability of their molecules to move. But there's also another rubric that we can use, and that is, what are the interactions between molecules holding these molecules together into their shape? And that's called potential energy. So what we can do is we can say, okay, what attractive forces are holding all of these molecules together? And we're going to call this potential energy, or PE. Now, because the solid is held together, there must be something holding those atoms in place, right? If there wasn't something holding them in place, then when you hit the table, all of the atoms would scatter away, kind of like you were hitting a box of marbles, or a pile of marbles or something, right? But they don't. They stay sturdy. They stay firm, and you can't hit through the table. With a liquid, if you put your finger into the liquid, the molecules move apart, but they don't spread in all directions and just escape forever. They then just bounce off the side of their container and then bounce against you or whatever. So there is some small attractive force in here. Which means that the potential energy is lower in a liquid than in a solid. In a gas, there's virtually no attraction between the molecules, and we say that there's virtually no potential energy between them. So if I take all this and go down here, I can write these like this. And so now I have a rubric. If I go in this direction, I end up increasing potential energy as I go from gas to liquid to solid. If I go the other direction, I end up increasing kinetic energy. So as kinetic energy increases, potential energy decreases. And as potential energy increases, kinetic energy decreases. So they work opposite of each other, these two types of energy that we are describing. Kinetic energy is the energy of motion, how mobile are things moving. Potential energy is the energy of attraction, how strongly are things attracted to each other. And so that's going to be how we define our phases here. So again, to summarize, things that move around have high kinetic energy. Things that have high potential energy don't move much at all. And so that leads us just to these. This is just the description that we just talked about. So solids are fixed and have rigid shapes because they have high potential energy holding the atoms together, and low kinetic energy because the atoms are essentially stationary. Gases are the opposite. Gases have very, very high kinetic energy, so they have very, very, very low potential energy. And then liquids are roughly the same. Liquids have some kinetic and some potential energy. They are the midpoint. So early on in this chapter, what we're going to do is we're going to study gases having very high kinetic energy and essentially no potential energy. They don't stick to each other at all. The gas particles just expand and fill their container. Kind of like if you blow air into a balloon, the balloon expands. The balloon does not stay deflated and all of the air goes to the end of the balloon. The molecules in the balloon that you've inflated have no attraction to each other. They have no potential energy. Virtually none. All they have is kinetic energy. They're just moving around. All right, and there's the homework practice for that discussion, which is just going to be a bunch of questions about which of these could be a gas. It has low kinetic energy and high potential energy. What phase is it? What's the difference between a liquid and a solid, and stuff like that. So, all right. So let me know if you have any questions about those topics. Those are pretty straightforward. It's just a different way of thinking about how matter behaves. And we're going to use that as our foundation to talk about gases. So now that we have a picture of how gases behave, which is just a bunch of molecules flying in all sorts of directions at once, let's talk about how gases behave in more detail. So if I go over here, let's actually put this question on the screen here. If I wanted to measure a gas, we'll say, here's my container, and I have gas particles inside, and they are doing their thing where they move in random directions. Here's one, bonk. Maybe this one does this. This one hits this wall. And so on and so forth. Everything is moving. Nothing is stationary. There we go. I think everybody is moving now. Oh, no, these two aren't. That's okay. There's our gas. Everything is chaotic and random. What sorts of things can we measure about our gas? So the first thing that we want to measure is the space that it is trapped in. We're going to call that its volume. And the variable we're going to assign to volume is V. The next thing that we're going to measure is how fast the molecules are moving. Because if they're all collected with each other and they're all bouncing into each other, eventually they should more or less all be going the same speed, right? Well, it turns out that we have a term for that. And that term you have heard of before. But you may not have realized that's what it is. Temperature is just how fast molecules are moving. So when you go outside and it's 80 degrees Fahrenheit outside, those molecules are colliding into you much faster than if you go outside when it's 50 Fahrenheit out. And the way that heat travels is that either you have less energy than the molecules bonking into you and you absorb their heat and then you get hot, or you have more energy than the molecules bonking into you and they absorb your energy as they bonk off and go faster as a result, and you lose that energy and then you feel cold. That's where temperature comes in. Temperature is just the transfer of random radiant energy and can be estimated for our purposes by approximately how fast the average speed of molecules are. We're going to just translate that to a Celsius or a Kelvin temperature for this unit. The next thing that we can measure is whenever something impacts the wall here, it exerts a force on that wall. If you punch the wall, you exert a force on it. If I were to punch the wall multiple times, somebody will come yell at me for what is all that racket, right? But I will be applying more force, especially if I had 1,000 people pounding on the wall or 1,000,000 people pounding on the wall. The force exerted by the gas on the walls of the container is called the pressure. We're going to talk about pressure in a little bit. You've probably heard of atmospheric pressure. What causes atmospheric pressure? It's the number of molecules pushing against you from the atmosphere above you. The atmosphere is not uniform. If it was, weather would be very, very boring. In some places, there's high atmospheric pressure and there's lots of molecules pushing down on you. In other places, there's low atmospheric pressure and there's relatively less molecules pushing down on you because they've been displaced by air currents or whatever, because gases are in motion and the atmosphere is dynamic. It's moving around all the time. You've probably experienced this on an airplane. Your ears, back when we actually flew on airplanes, right? Your ears have a diaphragm in them, which is your eardrum, and the air on the inside and the air on the outside may or may not be the same. We'll draw a picture of that in just a second when I talk about pressure on the next screen. And that has impact. So, you'll get a bubble in your ear, which you then have to, plug your nose or tug your ears or whatever to try and deflate so that you can hear again. All right, there's one more property that we can measure, and that property is how many particles are in here. And that would be the number of molecules, which will denote n. Now, lowercase n is actually going to indicate the number of moles of molecules. Because gases are small, and it doesn't take much to trap in a mole of gas particles. It's a little larger than you think, but it's not like your entire house only holds 1 mole of molecules. No, it's more like 10 2-liter bottles is enough for a mole of air, for example. Roughly speaking. 10 or 11 or so. So those are the 4 variables that we're going to measure. We're going to measure volume of gases, we're going to measure pressure of gases, we're going to measure temperature of gases, and we're going to measure how many particles are in the container as the number. And so I've listed those here. All right. We'll also put down the variables here. So pressure is P, volume is V, temperature is T, and the number is lowercase n. You'll notice that n is lowercase. There is a specific reason for that in physics. You don't need to worry about that too much. Just remember that n for this equation that we're deriving in just a second has to do with number of particles as moles, and it is lowercase. Now, what the heck is pressure? Let's talk about pressure in a little bit more detail. When you stand anywhere on the ground, there is a column of air pushing down upon you. And that column is roughly 10,000 kilograms worth of air. Now, even though particles can move in any direction, they're still subject to gravity. That's because they're made of matter, right? Everything is attracted to other matter, and thus even gases will eventually be attracted down to the Earth. So if this is my surface of my Earth, and here's my gas particle, it might end up doing something like this, but the entire time, gravity is pulling it down, and then it will eventually come back down to the Earth, assuming that it doesn't hit any other things along the way, which of course it will. But generally speaking, all the molecules that get bounced around do return to Earth. We do not lose all of our oxygen out into space, although technically some does escape. The atmosphere around the Earth does slowly, very, very slowly disappear because some of the particles escape its gravitational pull. But 99.9999999% of them are heavy enough that they fall back to Earth. So you don't have to worry about suffocating because all of the air just flew away. Oops, I want to keep this part. So what that means is that at any given moment, you are feeling the weight of 10,000 kilograms of air being pushed down upon you. So if it ever feels like too much, like you're carrying the weight of the world on your shoulders, don't worry, you're only carrying 10,000 kilograms of air, plus whatever else it is you're carrying. And when you look at it that way, it doesn't seem so bad. If you can handle 10,000 kilograms of air, you can handle anything. You can do it. Likewise, if somebody asks, do you even lift, bro? You could say, yeah, 10,000 kilograms of air every second. That's a lot. That's a lot of air. Now, this pressure is assumed that you are standing at sea level. There's no way that the middle of Minnesota or North Dakota or whatever this is on the map is at sea level. So sea level would be along the coast over here. We'll draw a little picture. So here's the sea, and then here is sea level. If you are standing here at sea level, and this is the edge of the atmosphere, then the pressure that pushes down upon you, that was the worst arrow ever. I'm going to redraw that. That offends the senses. There we go. The pressure of the atmosphere is equal to a value of whatever this mass is over this area. And we've defined that in the following way. You might think that this is kind of a dumb definition, but it's kind of ingenious also. Since there is one atmosphere directly above you, we define that pressure as such, 1 atmosphere, or 1 atm. Now, let's suppose that instead of being at sea level, I'm going to make the sea a little smaller. Here. There it is. You are on a mountain. That's not a very good mountain. Hold on. I'm having a bad art day. That's okay. So, there we go. Now I am up here on the mountain. So maybe this is like Denver. And the elevation of Denver is about 5,280 feet. That's why it's called the Mile High City, right? It has an elevation that's way up there. If I were to draw the atmospheric pressure here, well, the atmosphere doesn't just go up because Denver is higher up. No, the atmosphere is constant. It's at some height well above Earth's surface, right? So if I draw the atmospheric pressure here, there's significantly less of it pushing down on you, right? And so the pressure up here would be less than 1 atm. Just so we all remember, less than is where the arrow points to the left. Remember, the alligator eats the bigger number, right? Now, practically speaking, that has a number of applications. You might have experienced elevation sickness if you had a layover in, say, Denver, or maybe you've flown to, like, South America and visited the Andes Mountains in Chile. The Andes are very, very high in elevation, and if you travel around up there for an extended period of time, that can really get to you. Now, I don't know what you're doing in this class if you have the ability to go travel to the Andes. But if you do that someday, be advised that, like, traveling to very high elevations and not acclimating to them can cause health effects. One time when I was flying, I flew out of Seattle and I landed in Denver. But because of some issue, like I had either missed my flight or my flight was delayed and my connection was canceled, I had to spend the night in Denver. And I remember getting off the airport and walking around, and like I was not okay in the airport. Like I felt like I was gonna faint, and it was because of altitude sickness. And like I'd never experienced that before. I've stopped over in Denver a bunch of times, but I was probably dehydrated that day, or I was sick, or something like that. And then when I got off the plane and like had to wander around the airport to get to the hotel, um, I very nearly needed help. We'll say, like there were points where I felt like I might have blacked out. And that was due to the altitude, because the atmospheric pressure is way less up in high elevations. Now, when I say way less, what I mean is it's like 0.9 as opposed to 1 atmosphere. But we're very sensitive to elevation changes. Another example of this could be if you went swimming in the sea. Let's say you dove down 10 feet. And you can accomplish the exact same sort of situation if you swim down into a pool. If you've ever gone swimming and then you dive down to the bottom of the pool, you notice that the pressure you feel in your ears as you get all the way down to the bottom, like it hurts, right? It hurts a lot the deeper down you go, especially as you get older. Like I don't know if I can go down that deep because it would just give me a migraine real quick. And the reason for that is when you're in the water, not only do you have the pressure of the atmosphere pushing down on you, but now you also have the pressure of water pushing down on you too. Water is way denser than air, so you feel the effects of it much more quickly. And as you go down, that pressure compounds, and where you feel it most is your eardrums. So these are all effects of pressure. This is mostly just me trying to explain that pressure exists. It is something you can observe, and it is a function of elevation. So the lower your elevation, the higher the pressure. And the higher the elevation, the lower the pressure. And when you go flying in an airplane, you're like way up here. You're way above this. And the cabin that you were flying in is not exactly 1 ATM. It depressurizes a little bit due to like leaks and stuff. And so that's why your ears pop when you go up. And then they pop again when you go back down because the pressure normalizes. All right. So again, atmospheric pressure is defined as the pressure that you experience at the surface if you were at sea level. All right. And we've already talked about all these examples. So you can go higher in elevation, you feel less pressure. You go lower in elevation, you feel more pressure. Other units of pressure exist, which you've probably seen in various applications. The one that's used in science all the time is the torr, or the millimeter of mercury. Those are the same thing. Torr is used in, for example, blood pressure. When you measure somebody's blood pressure, you are measuring it in millimeters of mercury. So, for instance, if I got my blood pressure taken, and my blood pressure was 120/68, for example, that mean I don't know what the numbers mean. I know one's like systolic and one's diastolic, but I don't know what those terms mean. It has to do with your heart like beating and pulling and blood. I don't know. But for whatever function is going on with your blood pressure, one component of it has a pressure of 120 torr, and the other one has a pressure of 68 torr, or whatever the numbers were that I said. So knowing what millimeters of mercury is kind of useful. Not that you would be measuring somebody's blood pressure in atmospheres because you get like 0.16 or something, and that's weird. If you told me that my blood pressure was 0.1, I would be concerned. The other unit of pressure that's commonly used outside of science is the PSI, or pounds per square inch. This is used in engineering and in things like tires. So if you measure your tire pressure and you put the little gauge in there, it might say 30 psi or 35 psi. What that means is that the amount of air that's in there is measured in, this is how many pounds of force the air is pushing against your tire wall for every square inch. So if you drew a 1 square inch area on your tire wall, the air inside is pushing 30 pounds of pressure against that if you have 30 psi. Now, for a 30 psi tire, you can see that 1 atmosphere is about 14.7 psi. So that means that there are about 2 extra atmospheres of air inside your tire. Now, interestingly, if you had only 1 atmosphere of air inside your tire would be considered to be completely flat. And the reason for that is because if this is your tire wall, tire on the left and then outside on the right, and I have 1 ATM out here and 1 ATM out here, there's no difference, right? There's nothing pushing out this side. The force on both sides would be equal. So what I have to do is I have to add extra in here. Now I have way more than on the outside. And so now my tire will push against the, or my air will push against the tire, which will then keep my vehicle above the ground. So beware that, like, for gauge pressure and on tires, the 1 ATM that is part of the atmosphere will be already accounted for. And that if you don't have any air in your tire and it's, say, flat, you don't have a vacuum. You don't have 0 ATM in your tire. So now, because these are all units, you can do dimensional analysis between them. So, for example, we'll just do a sample problem here. It may come up at some point that you will need to do an activity like the following, where it's like, okay, on my Jeep Wrangler, the recommended tire pressure is 35 psi. Okay. What is that in atmospheres? Okay, well, we can turn psi into atmospheres. There is 1 atmosphere per 14.7. And then you just treat this like any dimensional analysis problem you've been doing so far. So you can convert between units like that. And you may have to, depending on the application. Some of the homework exercises will expect you to convert between units. You may have to do that on the quiz and so on. Okay, so you should be able to do that pretty straightforward. All right. We're sort of out of time today, so what I'm going to do is we're going to call it a day here. But when we come back, what we're going to do is we're going to explore those 4 properties that we listed here. We're going to put a gas in various conditions and see if we can describe any sorts of properties that go between them. And by that I mean there are people who are very famous physicists who have had laws named after them based on these things that we're going to do. So we're going to use balloons, we're going to inflate them with gas, and then we're going to subject them to various conditions that manipulate variables. So for example, in this first one, I'm going to put a balloon in a vacuum. And I'm going to suck all the air out from around the balloon. The air inside the balloon will remain because it's trapped in the balloon. But the air outside the balloon will be removed. And we're going to see what happens. And then we're going to inflate it again. And we're going to just play around with it. We'll change its temperature. We'll inflate the balloon. Like so on and so forth. And as we do that, we're going to learn all of these things are related to each other. And then we're going to construct a formula for it. But that's going to be for Wednesday. So I will be putting quiz number 6 online after class today. In fact, I should probably just type that down at the bottom here. Let me do that really quick. So quiz number 6 due Monday next week. What is next week? The 24th of May. Well, we're almost to June. Holy crap. And yeah, I think that's it. So make sure that you get your lab worksheet in by the deadline. Next class will be on Wednesday. We're going to probably finish up most of Chapter 7, if not all of it. And that's really all I have. So have a wonderful rest of your day. I will see you on Wednesday. Take care.